Hey guys, welcome back to the channel and this new tutorial on PyTorch. In previous video, we learned about RNN, like how they works and how we can implement them in PyTorch. In this video, we will learn like what are the limitations of RNN and how we can uh, um, solve them using LSTMs, which are also known as long short-term memory. Okay, so let us dive in and see what are the limitations of RNN. So there are two main limitations. One is they cannot handle long-range dependencies, and the other one is vanishing gradient. Okay, so let us see in like figure like how they are kind of having those issues. So first thing is like when we unfold an RNN for a sequence length, like let us say 100 words of a sentence. So it will be like a depth of 100 layers. And then when the first is computed and the hidden layer is passed to the next one, so the information that was at the first word is completely lost when it is at the end of the last token. Okay, so that's like it cannot handle long range dependencies. For example, if you are processing a paragraph to do a text classification, and in that sense the information that you get at the end of the encoding, it will not remember like how or what was the input information that was given in the beginning. Okay, and the next one is like in this figure itself. So you are kind of trying to train a model with a layer of 100 size. Like you could think of simply like you have a neural network with the depth of 100 layers, and then if the gradient is kind of small for a particular batch, it will be like zero when it will try to update the initial few layers. Okay, and that's the very uh, big problem in training RNN models. There are another problem which is also known as uh, which is also related to gradients only, known as exploding gradients. Like in that case, the gradient is too high in the beginning, and then it multiplied again and again with large values, and then the gradient becomes really large. But that is kind of a bit easier to handle. You can use gradient clipping and other techniques to avoid the exploding gradient, but vanishing gradient is something that is really hard to handle, and that's what happens in case of vanilla RNN. That's why it is not very much recommended to be used in general, and that's why LSTM and other variants of RNN are quite popular to be used. Okay, so let us see like how LSTM can resolve it. So LSTM simply uses some gated mechanism. So it uses three gates to control the information flow, and those are known as input gates, target gates, and output gates. Okay, so they are simply like um, linear layers in a sense. So you have two weight matrices in the input gate, and then two weight matrices for forget gate, and two weight matrices for output gate as well. And then we have one more linear layer that is used to generate intermediate state. You can think of it like a linear layer that is learnable, and it is used to generate intermediate state that is used to compute uh, cell state and then hidden state. Another another important thing that you need to note here: instead of just having one hidden state, you have another cell state here. Okay, and this is known as long term memory, and this is like a short term memory, this HT. So it is like it is updated every each and every time when input comes, whereas the CT is has a bit more controlled environment, is surrounded by. And this is how it handles the long-term dependencies, because it has a mechanism to control the information flow. Okay, so let us dive in and see how we can use LSTM in PyTorch. So this is the code that we have written for simple RNN. So what we will do is simply reuse it, simply change it to say LSTM network. Okay, just refactor it, and we will simply change it to NN.LSTM. And now we are using LSTM cell. The inputs are exactly same, like you have input size, hidden layer, and number of layers, and then bidirectional for and false, and batch first is true. So if you haven't seen the previous video, check it out so that you could understand it more properly. Also, just to mention here, when we say he is handsome and the features are of size, let us say here we are saying size 2. So what we are passing is here is the word embeddings, not word itself, for those who are like quite new in this uh, NLP domain. So for them, it is like we have embedding layers beforehand. Okay, so that is excluded in this tutorial. So what we are getting here is after the embedding layer, we get like so the raw input would be like is handsome. Then we use one hot encoding where we get the indices of each and every word, and then we pass through them via embedding layers, and that's how we get the features. Okay, and that's where we are, that's what we are using it to not make it too much complex, so we didn't put that part in this code. Okay, and another thing is that the output we get from the LSTM layer is as we have seen like here. So what we get as output is this and this as a hidden state, and definitely the output, okay, which is nothing but this. One more difference is like instead of passing just one hidden, we need to pass a tuple here. Okay, so that we will change here as well here. Okay, and that's how it is different. So here we are passing hidden state as well as cell state. So this is like hidden state. It will be the same size. That's why I just copied it. But the first one is hidden state and the second one is cell state. And this hidden state is also like hidden state and cell state for the last, I mean, after the last layer. Okay, I'll just run it. So you see here is our final output. So as we have like two inputs, so we have like two samples, each of with three segments, three words, not segments, and then each word we got as a final output, like what is the hidden size of the LSTM. Okay, it is quite similar, exactly what we get from the RNN, vanilla RNN. Okay, and the hidden output are this second output is two matrices. You can see here, this is like the first one, which is nothing but the hidden state from the after the last input, and then we have this cell state, which is after the last. Okay, they are also like same size, like number of layers, batch size cross hidden size. Okay, so we have batch size 2, we have one layer, that's why we have just one. If there is a more, it will be other matrices there as well. And we have batch size of 2, so it is 2 cross hidden size, which is 3. Okay, so I hope that is clear, like how it is working. Now let us dig a bit deeper and see like how it is actually implemented in PyTorch. Okay, so let us print this, the parameters, and let us run and see the output. Okay, okay, so now it looks a bit different than what we have seen in simple RNN. So it is kind of a little smart implementation wise. Okay, so what they did is simply, so for input to hidden layer, so if we look at the equations, so we have weight matrices multiplied by input. Okay, so what they did is they simply batched this part, this part, this part, this part in just one matrix. You see, that's how it is a bit smart, or not quite smart, I would say. So this first part, this 3 cross 2 is, that is this WII and so on. So you can have WIF, WIO, and then WGI, IG. Okay. And then similarly, we have this also batched together for the second part of the equation, where you have WHI, HF, and this is like HH, it is called here. Okay. And then if you have an input which is of the size, let us say 2 cross, so let us say here we have 2 cross 3 cross 2, and if you simply transpose it and multiply it, it will give us the input for the next state. Okay, so that's how it is, quite intelligent way of implementing it. Okay. Okay, now so let us look a bit deeper in the equations a bit more carefully. So what is happening here is, so we have three gates, which is input, target, and output gates. And then we have an intermediate layer to compute this intermediate state. And then we have this cell state, which is computed with dot product of target gate and the previous cell state. Okay, and then we also add it with input gate with this GT, or you could say this is a linear layer that is processing our input and hidden state to get intermediate representation, and then we are passing it through the input gate. Okay, so this is the part where we are controlling the flow of information via input gate, and this is the part where we are controlling at how much information we need to pass it to the next cell state. Okay, so this way we are kind of generating the cell state, the new cell state. Okay, and the next part we use this new cell state, and then we simply apply 10H on that, and then multiply it with output gate to get the new hidden state, and it is also the output state. Okay, so it is like output representation for our word that we are getting as a final representation. Okay, so I hope that is clear. If you have any queries or question, ask in the comment section. I will try to address them. Okay, so I hope it is clear like how LSTM is working. So we will stop in this video. In the next video, we will learn a bit more advanced um, RNN type, which is ZRU, where we don't use any cell state. I mean, it is memory less like RNN, but it has gates compared to RNN, but it only uses two gates. One is reset gate and another one is update gate. Okay, so we'll see in detail in the next video. So thanks for watching. Bye for now. Take care. See you in the next.